Yeah, my name is Vinayak, and today I'll be talking about Bluetooth low energy controller in Zephyr. I have like two parts to my presentation. The first half is going to be introduction, so it's going to be like introduction to Bluetooth low energy, what it is when I say it's Bluetooth low energy, how it is implemented in terms of basically the technology as such, not anything to do with the code. And the second half would be the design or the architecture which I'm currently working, which is to improve on what is upstream already. I'm not going to take time explaining the old architecture, but the new one is reusing most of what is there upstream and what's going to come in Zephyr. Before I start, may I ask like how many of you here is using Bluetooth Low Energy, and then okay, and how many of you actually develop Bluetooth Low Energy? That is basically the host or controller or application or profiles. Okay. So since I see that most of them are users, I guess the first half would be interesting for them to know what's happening underneath when I talk about Bluetooth low energy technology. Before that, I will just start with, I was supposed to have a clicker, yes. So as I said, introduction. So I've been developing Bluetooth both BR/EDR and low energy from the time I have like passed out of my university. In between, in the beginning, I was also doing a bit of Windows applications and ASP.NET and stuff like that. But what I am doing today is I'm primarily the active contributing maintainer of the controller in Zephyr. Prior to which, and also as a consultant to Nordic, I have been developing the in-house Bluetooth stack in Nordic for the last 10 years. I have moved back to my hometown in Bangalore, and I continue to be a consultant for Nordic. I will be a bit fast because I'm already into my 5 minutes into my presentation, so I will probably go fast, and I prefer to basically show demonstrations in the time I have. So Bluetooth, what is it? It's basically short range, low power, personal area networking communication, or something that is between your watch and headset and your phone, and probably between your TV and your remote and so on. So it's like just a short range communication stuff, like maybe up to 100 meters if you have 20 dB TX power. It's in the 2.4 gigahertz ISM band, which is basically free to use. The special interest group was formed in 1998. It's over 20 years of Bluetooth around you, and if you have a scanner or a phone, if you just scan now, you might get over 200, 500 devices just around you sitting here, which are advertising, and probably all your car kits and headsets receiving calls and stuff is actually using Bluetooth and BD, basic rate and enhanced data rate. So there's billions of products shipped, and there's over 33,000 SIG members who are basically contributing and using the specification. What is Bluetooth low energy? It's ultra low power, so it's even lower power than the basic rate. It's optimized for short burst data transmission, which means that it's very small packets that's on air, and very short RX and TX windows. The main idea was race to idle, which is basically you turn on the radio as seldom as possible and turn off the radio as soon as possible. With this, you can actually achieve like a connection, transmit data, and tear down within like 6 milliseconds. So a device can advertise and be scanned by a second device and connected and transmit some minimum data and then tear down by 6 milliseconds. When I started, it used to be before the profile or the specification was adopted. It was called like a sensor profile, and it just mentioned about value, like a parameter and value. All that you wanted was this is the parameter, this is the value you want to transmit. So it is by the time it was adopted, we basically had layers of modules or components in the stack. So it's still simple stateless operation stuff. So the information is transmitted as a parameter and a value, but you still have a lot of other infrastructure around it. It was supposed to be a low memory footprint. So I think the thesis that introduced Bluetooth Low Energy Vibri basically mentioned that the whole implementation could be done in 4 kilobytes of ROM. Yeah, but that was then. Yeah. And then you should be achieving about over a year of coin cell battery. So it's like CR2032 cell. You should be achieving a year or more of battery life. So moving on to the technology, what's underneath it, the BLE stack look as shown here. So at the bottom, you have the PHY, which is basically the 2.4 gigahertz. And then there's the link layer, which basically implements the roles and states, and a standard host controller interface specified in the specification, which then can be used by hosts like Zephyr host or BlueZ host to basically achieve a connection with a peer device and so on. And then in the host, you have the L2CAP, which is a logical link control adaptation protocol, over which you have the attribute protocol. As I mentioned, the parameter value is actually exchanged over attribute protocol. And then for the security, you have the security manager protocol, and GAP is the generic access. So that is what is used to basically recognize a device and establish a connection and so forth. On the top is the profile. That profile is basically user use cases and stuff like that. So head over, GAT is used by your keyboard and mouse, proximity, your proximity tags. Of course, the keyboard and mouse will have batteries, so then you have a battery profile to exchange the battery level and so on and so forth. So there's temperature, heart rate, blood pressure, and yeah, now there's like tons of them. So on top of this, you have your unique application. So how you would basically differentiate from your competitors. On the BLE PHY, as I mentioned, it shares 2.4 gigahertz along with the BR-EDR. In BLE, you have 1 megabit symbol rate, 1 mega symbol per second. You also have 2 mega symbol per second signaling rate. The modulation is still GFSK, and you can have TX powers up to 20 dBm, and compared to BR-EDR, which uses 80 channels, BLE only uses 40 channels, and 3 of which is used for advertising. Which means that the device that wants to be connected would be advertising, and the device which wants to connect to this one is scanning on those 3 channels, and those are the 3 channels on which you would establish a connection. And once the connection is established, it happens on the 37 other data channels. And as you see, I have marked those advertising channels, and they're spread across so that they don't basically interfere a lot with the Wi-Fi channels. On the link layer stuff, the responsibility of link layer is to basically maintain the advertising state, scanning state, and then and be in slave or master role. The legacy advertising payload was up to 31 bytes. The extended advertising now supports up to 255 bytes. Plus, you can chain them to achieve longer advertising packets. But the advertising extension would then be using the data channels. So they will have a very small packet on the advertising channel, and then they will chain or continue with the advertising data on the data channels. On the data channels, the legacy PDU size was 27 bytes. With 4.1, 4.2, you can actually have 255 byte payloads, PDU lengths, and BLE has built-in AES 128 with CCM. So all your data exchanged would be encrypted. Okay. So this is just a small animation of what's happening with respect to advertising. So let's say we have a device A. Yeah. So we have a device A that I didn't move. Yeah. So so we have a device advertising at 20 milliseconds, and they are advertising on 3 channels every 20 milliseconds, and we have a scanner which has a window of 25 milliseconds, I think, and it scans on channel 37, and then has an interval of 50 milliseconds, so it then scans on 38. So in the first scan window, the scanning on channel 37 is able to capture 2 packets, and the second window, the channel 38 is able to see 1 of the advertisement on it, and the third one. So this is what you would see on air happen when you have, if you turn on your phone and scan for devices, it will receive packets whenever it sees the advertising on those channels. The topology, a scanner, and then you have an advertiser. Advertiser is advertising. A scanner would be listening to the advertisement. The scanner, if it is in the initiator role, would send a connect request packet to the advertiser, and then the connection is established. So basically, a scanner becomes an initiator and becomes a master. A advertiser would become a peripheral if it is in a connectable advertising. So similarly, you can actually have a master connect to many slaves. If the master is also a BR-EDR device, it can then have a BR-EDR connection. And you can also have a scatternet scenario where the slave can be another advertiser and be connected by another device. Yeah. How does the connection look like? So once the connect request has been sent, the connect request will contain an offset from the time the connect request was sent, where the master would transmit with an access address, which was also mentioned in the connect request. The slave is listening at that interval. Once it receives a packet with the correct CRC, it's going to basically use a small duration to turn around to be a transmitter. So that small amount of time by specification is fixed at like 150 microseconds, and it's called interframe space. So between RX and TX, or TX and RX, you always have a 150 microsecond space. And if nothing is there to be transmitted between the slave and the master at that interval, then the radio quickly goes to idle. So a packet here, like 27-byte packet, it would consume like 328 microseconds, and then you have a 150 microsecond gap, and then another 27-byte, if received, would have another 328 microseconds. So around 806 microseconds is what there is the transmission or use of radio there. And then the next interval, it will repeat the same. The master will start with the transmit, and the slave receives it and transmits its packet back. And if there are more packets, they keep continuing that with the 150 microsecond gap until the next connection interval, and they can keep on going on as long as there's data. So, how do I show this in Zephyr? So let me just, I have my boards here. I have two Nordic semiconductor development kit. I have the latest 52840 chips, and I also have the 52832, which I have connected to the power profile kit. So I hopefully will be able to show whatever I showed you in this graphics. I should be able to show it natively on Zephyr, because I have the GPIO debug enabled and upstream. If you enable them, you will be able to use any logic like an oscilloscope or a logic analyzer to see what I showed in this graphics here. So let me see if I can. Let's go to capture. So before that, it's important I show what I'm doing. So, all right. The problem is I don't know. I don't see what I'm doing. All right. Okay. Let's see. So typically, the make menu config has a section for Bluetooth.
Sorry, could you make that bigger?
Let me see, how can I do that? Is there a bigger?
I'm doing it.
Was it, what was the key combination there?
Again, bigger. One more.
Control plus,
Yeah.
command plus. It's control
Command
plus.
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 Command plus. Yeah.
Okay. Yeah?
Yeah.
Okay. Fine. So then there's a section for Bluetooth, and you just go down. Yeah. So in the Bluetooth link layer, there's of course I'm having the source base which I'm working now on the new architecture. So the old one is available as a software-based BLE link layer, and then the new one is basically the architecture is now split into two different layers in the implementation. I will come to it why it is that way. And what I would usually do is I would go down, and there's something called Bluetooth controller debug pins. There's also profile radio ISR, which basically prints how much CPU time is utilized by the controller in its radio ISR. But usually this should be sufficient to enable the GPIO toggling and use a logic analyzer and measure how much of CPU time is utilized by the controller implementation. So it's already built. I don't know which one is peripheral, but yeah. Let's see if things are working fine. Okay. All right. So what I have here. So I already have a connection. So let me just start capturing this, and I will reset one of the board and I will reset the other board. So I have a master and I have a slave or a peripheral. So when I reset, one of the board is advertising, and the second board is scanning for it. As soon as it finds the heart rate profile in the advertiser, it's going to establish connection. So it should have already happened, as I said. Just stop this. So if you see all this break here, that's where I press the reset button, right? And this is where the scanning is happening. Since I already had a connection, the connection needs to have a supervision timeout before it starts advertising. So, so this was a previous connection where I kind of like reset one of the board, and the other board was not reset, so it continued to like go into supervision timeout. This is where the slave. Wait a second. Yeah. So this is where the actual chip startup, and there's advertising going on. So there's advertising and there's scanning. So there was no advertising that coincides with the scanning here. So appears like this is where the advertiser was discovered by the scanner, and then from this angle I can't make out, but yeah. So this is the initiator here, and let's see. So this is the place where the connect request was sent by the initiator, and this is the first EU connection event, and henceforth you have the connection events where the RX and TX are being exchanged here. So these are the radio interrupts, and if I zoom in, then you should be able to measure like the amount of time it takes, or the CPU time used to used by the controller for the radio ISRs. So that was right. So this is just the stuff. So going to the controller. So the controller was contributed in 2016, and since then I've been basically running it through the conformance tester, and because the conformance tests also, which is defined by the Bluetooth SIG, undergo basically enhancements and fixes to them. So I had to basically catch up with the conformance tests and run through all the conformance tests for Bluetooth 5 specification, and it was we basically got a design listing for it for our DK, the development kit, in October 2017. So what you have now on the upstream Zephyr is actually a qualified design for the controller component. What it has is it's fully BLE 5.0 compliant. It has unlimited roles and connection count. What that means is that the RAM permitted, you can actually, I think we have set a upper limit of like 64 as a count in the kconf. But if you could go more than that also if you want, and it's only restricted by the RAM. it also supports concurrent multi-protocol ready, and it has intelligent scheduling of roles. So if you have a device that wants to establish 8 or 16 as a master, connect to 16 peripherals, the scheduling is going to arrange them in an order such that these connection events don't overlap. So it establishes connections equally spaced in time, and also if you do a connection parameter update, it's going to find a non-overlapping offset and then maintain the connection there. And also as a slave, if a single device is a slave to more than two masters, and since the slaves depend on the master clock and they would drift into each other, the current implementation on the upstream master is able to detect that and then do an auto connection update to move them in a non-overlapping intervals. It's also the design is I just say it's portable, but since there is only Nordic chip there, but yeah, it's open for other vendor silicons to implement the hardware abstraction layers. Okay, how does the architecture look of the controller? So at the bottom you have the SoC. There is a barebone hardware abstraction layer. Earlier in 2016, most of the hardware in the SoC was accessed using the hardware abstraction layer. But the goal is to move or remove the hardware abstraction layer and use native Zephyr drivers from the controller code. So above the hardware abstraction layer, we have something called a ticker, which is responsible for this periodic scheduling of the advertiser scanner and the connection roles. Utility is barebone implementations of queues and FIFOs and a very lightweight memory management. It also has a small module that I have developed called Mayfly, and the idea behind is basically race to idle. So it's just a way of executing functions across interrupt priorities. The link layer is the core implementation of the packet transmission and control packets and stuff like that. Above which is the HCI, and then you have the host, Zephyr host, and application. Right. The goal is for the new architecture is to have a multi-vendor support, which means that vendors would like to basically add in their BLE support at various layers in the controller. So the split is such that if vendors want to basically have their own packet management in let's say it could be in their silicon or it could be in a binary blob or so, the new architecture would permit them to basically reuse probably mature implementation that they already have. So like in the previous presentation, they said that they have a coprocessor and then they have softwares in it which they have been using for many years, and probably they continue to use it because of it being mature. So the new architecture would permit vendors to basically replace at various layers in the control in the controller replace the modules and add in. So here on the top, it's the application, then the host, which is both Zephyr threads, and then there is an upper link layer which is going to be open source, and it would have all the control procedures and scheduling of the events, radio events, and so forth. And then there's a split. You have the lower link layer. In case of Nordic, it would be open source. The lower link layer is nothing but the radio access, how the TX and RX and the packet being exchanged between the two devices. And then there is the hardware, which is basically in the SoC. And yeah, the vendors could choose to reuse the lower link layer if they want. Then they would just have to abstract the hardware interface, or they could just utilize the API between the upper link layer and lower link layer, which is I can in the next slides I can show what those are. Right, Mayfly. So if I go back, so there is a mention of tasklet there, but actually it was a goal that probably we will have something equivalent in Zephyr that could be used in the controller to execute raise to idle functions and so on. So until then, we do have something, but I haven't ported it yet to the native implementation in Zephyr yet. Until then, there's a small implementation in the controller which basically is something like a work. So if you have a thread in Zephyr, you could have a work which is executed by a work queue. So what is a Mayfly? Mayfly is similar to a work in thread, but it's basically scheduled by an ISR and executed in an ISR. So I try to represent that in the diagram there. So you have callers and callee, and all of these are either thread or ISRs. And a caller would request to schedule a function. It's just a normal C function, and would request that to be scheduled in an ISR at the priority it wants it to be executed. So each ISR has a queue of functions to which the caller would enqueue it, and then trigger the IRQ to basically process those functions. This was something that I had hand-drawn like way back in 2012, how I actually visioned the controller to behave with respect to handling the radio. So at the bottom there is a thread. The T represents the thread. So thread is going to basically make some API calls, and there is going to be a level of execution there where basically like a job that would basically do the scheduling stuff, and then have a higher priority context that would basically access the hardware and set up the radio and so on. I don't want to go into the detail. The topmost is basically the counter compare registers firing as a consequence of the setup done by the job. And then there's a radio interrupts happening as you receive and transmit the packets. So what's happening on the scheduling in the new architecture? You can see the bigger blocks are the execution context. There's host, and in the center you have the upper link layer, and then on the rightmost side you have the lower link layer. When you want to start advertising, then the API is API from the application would then translate into HCI. The HCI would then okay, so this is the HCI. HCI would then call the link layer interface to prepare a scheduling message that's placed into a queue here. The upper link layer would then set up the counter compare registers. When the compare triggers, then the requests are then placed into a pipeline, because you could have overlapping schedules. They will then be placed in a pipeline and then they would basically schedule the preparation for the radio event in the lower link layer. Once the radio event is finished, which is basically to do the packet transmission and reception, there would be a message sent back to the upper link layer saying that that particular event is finished. The upper link layer would then look into the pipeline to see if any other overlapping events are there, very back to back or very close. then it's going to basically run the lower link layer again. On the TX path, again, there would be a HCI command, which then goes into a fixed size, fixed length FIFO. That's because in the HCI you have like a read buffer size. If you say, for example, 10 TX buffers, then the 10 is going to be shared across your connections. So all that is needed is just a fixed length FIFO for the TX. But then once it's received by the upper link layer, it's demultiplexed into connections. So if you have 10 connections and you had 10 TX packets, each one for those connections, then they are basically demultiplexed into those connection contexts. And when a connection event occurs, only that packet is utilized by that event, transmitted, and then comes back in a FIFO here because the num completes would at max be 10, because that's what was configured in Zephyr, that you would like 10 TX buffers. Okay, and there's a FIFO here, there's a FIFO here. So the only difference is there's a FIFO going downstream, but then demultiplexed into context safe queues, and then there's a FIFO back receiving the number of completed packets down to the host thread. Yeah, that's on the TX path. And yes, on the RX path, the host thread will always fill up a free FIFO with free buffers, which would be picked up by the radio events, and then the received packet is then sent down to the upper link layer, which would parse it to see if they are data packet or control packet. If they're control packet, then they will have a special processing being done. If it is data packet, then it would be sent to the HCI layer and then host. Okay. So I will like to show. I just have the power profile kit, so I can show you the power profile. But before that, I already have some screenshots of how it looked, how it looks upstream with respect to the architecture there. So at the top is basically a zoomed out power profile stuff where it's doing continuous scanning, but you can clearly see that there is a lot more CPU idle between channels. So these are like 37, 38, 39, 37, 38, 39. But then there's the multi-role where you also have advertising while scanning. As you see here, the advertising actually utilizes one whole, or is basically replaced a scan window here to do the advertising, and then the scan in the next scan interval is when the scanning is happening. But with the new work which I am doing, the scanning basically utilizes very little time to switch channels. So it's like from 70 to 300 microseconds to switch the channel to do the scanning, and advertising at the same time is basically pipelined here. So and has a resume. So as soon as the advertising is finished, the scanning continues back to back with after the advertising. So this means that the radio utilization is higher in the new architecture compared to the old one. So these are just the points, like continuous events for continuous scanning and direct advertising are truly continuous. Excuse me. So, okay. I'll probably just take another 2 or 3 minutes to show if I can. Let's see. So I have this tool from Nordic Semiconductor, which has the power profile, which apparently opened up in this window again. So let's go up here. Okay, I will need to. Let's see. No. Sorry, I need to turn it on. Okay. It's not enumerating yet, so let's see. This probably doesn't need my help. My help? Okay. Yeah, I'll just give a last try and then. Okay. Yeah, it's probably, I must be having some wrong firmware there. So basically it's just going to have, it's going to display whatever I displayed over there in terms of the power profile.
We believe you.
Yeah, because I have taken the screenshot, so yes. So I guess if you have some quick questions, I can answer. I'm always available on IRC, and you should be able to send me an email. Anything related to Bluetooth, I will usually look at in the Zephyr mailing list. So.
So the new link layer that you presented, the new architecture, lives in a private branch right now because of certain other items that we're not going to discuss here. But when do you expect at least the first bits of it being merged upstream so we can actually see these?
So I'm still porting all the control procedures. That's the remaining part of it, which I promised myself that it should be like 3 weeks. But I also handle bugs and requests on the mailing list. So yes, so that's what is consuming my time. But I would say that yeah, sometime in 3 weeks. But this private branch also is used to develop Bluetooth features, the future Bluetooth features. So SIG members would be given access to all the new work being done. But whatever is adopted, those will always be merged back upstream. So the Bluetooth 5 features, once I'm done with porting all the control procedures, should be, along with the new architecture, available upstream. Yeah. While the new features would be developed in the private repository, but it's it's not private as such. It's open for all the Bluetooth SIG members because of the Bluetooth confidentiality stuff.
Mm-hmm.
Yes. So thank you.
Thank you.